This is worksheet 2 of the atomic structure packet, and in this worksheet we are going to really just focus on the electrons in an atom and sort of leave the protons and the neutrons alone for the time being. Because so far we have just used a Bohr model from worksheet 1 to describe where the electrons are. And the Bohr model uses these circles or these shells, right? So here's a Bohr model, and we'll talk about why it's crossed out in a minute. And it assumes that these electrons move in these perfect little circles around the nucleus, some closer to the nucleus, some further away. And this is part of the story. But we can be a little bit more accurate than that. Okay, they don't actually move in these perfect little cartoon-like circles. What they really do is they are located in these areas of space that we call orbitals. Okay, you might remember from your atomic timeline project, there was this guy named Heisenberg, and he came up with this uncertainty principle that said that it's really impossible to know the exact location and the exact speed of an electron both at the same time. So we can't say for sure that one specific electron is found in one exact place at a given time. But what we can do is say, okay, here's a general area where a particular electron is most likely to be found. All right, now this idea of these circles around the nucleus getting further and further away that Bohr introduced is still helpful. Okay, the orbitals, these regions of space, are organized by the shell that they're found in. So instead of now just saying, oh, we find this electron in the first shell, right, this little circle, instead we're going to say, okay, well, yes, we find it in this first shell, but within that first shell we'll be more specific and we'll actually say which orbital or which particular region or location of that shell you would find it in. So there's sort of two pieces of information for each orbital. There's going to be a number and then there's going to be a letter. Okay, so if we look at the very first orbital, there's actually a picture of it here. Okay, the first orbital is the 1s orbital. So the 1 means that it's found in the first ring or circle around the nucleus. So if we went back up to Bohr's model, that 1s orbital would be found in this first energy level or this first shell. And the shape of this region of space where we can find it is described as an S. Okay, now that S means that it's a sphere. It's circular. Okay, and in that second energy level, the second ring, that second distance around the nucleus, there's also an S orbital, a sphere-shaped space where you can find electrons. But because it's in the second ring, or the second energy level, the second distance from the nucleus, we would call it the 2s orbital. Okay, so here is a picture of the 2s orbital. It's a sphere. It's three-dimensional. Okay. Now, the first energy level, that first ring around the nucleus, only has an s orbital. It's a pretty small region of space. But the second ring, the second energy level from the nucleus, is a little bit larger, right? You can kind of tell if you look up here, the Bohr model looks a little bigger. So it not only has an s orbital, in that case, since it's the second energy level, it would be the 2s orbital, but it also has p orbitals. Okay, why do we call them p orbitals? It has to do with their shape, right? Notice how the shape of a p orbital is a little bit different. And we say it almost looks like a figure 8, or like two balloons sort of stuck together. Okay, now there are actually 3 different p orbitals, because you can imagine that you could have a p orbital that's sort of on this horizontal axis facing this way, because we got to think three-dimensionally. So that'd be the px orbital. It's on the x-axis. And you could also have a p orbital that's on the y-axis, so we'd call that the py orbital. And then, I'm not great at drawing three-dimensionally, but you could imagine you could also have a p orbital that'd sort of be sticking in and out of your computer screen right now. Okay, and so we call that the pz orbital. Okay, so whenever you have a p orbital, like in the second shell, there's not just a 2p orbital, but we specify there's a 2px, a 2py, and a 2pz. Okay, so that second ring or energy level around the nucleus has a 2s orbital. It's got a 2px, a 2py, and a 2pz. Okay, now by the time you get to that third ring, you can look back up here, right? That's even bigger. Still, it's got an even higher energy, a further distance from the nucleus. So there, in the third shell, not only is there a 3s and a 3px and a 3py and a 3pz, but we also get these d orbitals. And you're not going to need to know all of them. There's actually 5 of them, and it's just like 3dxy and 3dxz and 3dyz, and the variables get a little crazy, but there's basically 5 of them. And they look like, as you can see here, sort of 4 balloons all stuck together. Okay, so I just want you to know that by the time you get to that third energy level, not only is there a 3s orbital and 3p orbitals, but there's also there's some 3d orbitals, and so it kind of just keeps going on like that as the energy levels get bigger. Okay, now with all this talk about all these orbitals, it starts to get a little bit hard to keep track of. So we can use a little graph, which a lot of you will actually in the future find pretty helpful. So we can organize all of these orbitals by their energies. Okay, because remember that just like with the shells, the more energy something has, the further away it is from the nucleus. Okay, so if we look at this graph here, right, and we graph the relative energy of these different orbitals, okay, the first shell around the nucleus can only have one kind of orbital. It has an s orbital, right? So here's our little 1s orbital. It's really close to the nucleus, so it has a really low energy. It's low down on the graph. Okay, so bear with me. I'm going to try to use different colors here. If that's our nucleus, okay, now we know the nucleus would actually be bigger, and it would have, you know, all these protons and neutrons in it. But that 1s orbital here, we would find right here, and it'd be a sphere, like 3-dimensional. Okay? And then as we got into the second energy level, it's a little bit bigger. And so we would find not only a 2s, but also the 2px, the 2py, and the 2pz. So all, basically 4 of those orbitals would be found within this distance here from the nucleus. Okay, and then as we get to the third energy level, we'd have a 3s orbital, we'd have 3px, 3py, and 3pz, and we'd have the 5 3d orbitals, 3dxy, 3dxz, 3dyz, so on and so forth. Right, and then the fourth energy level, that's where things really get crazy, because there's actually, not only is there 4s and the 4p's, and of course the 4d's, but there's actually also the 4f's. Okay, and there's like a ton of those, so those would be here, right? So we can sort of organize or group these orbitals together based on the energy level that they're a part of, which really just represents, you know, obviously how much energy they have, but how far they are from the nucleus too. All right, now we can actually start to draw a diagram of a particular atom by thinking about, with a particular atom, how many electrons it has. All right, so if we thought about carbon, for example. Okay, if you look on your periodic table, this isn't in these notes, but I'm just using this as an example. Carbon has an atomic number of 6, and it has a mass of 12. Okay, so if it's got 6 protons, because that's its atomic number, it's got 6 electrons also. Okay, now each one of these little orbitals, each one of these little boxes here on this diagram can hold a maximum of 2 electrons. Okay, and we're going to represent the electrons with little arrows. And we're actually going to draw, every time we draw an electron, one facing upward and one facing downward. Electrons actually have spins. They spin in a certain direction. So if you already have a clockwise electron in an orbital, there's got to be a counterclockwise one next to it, because if you get two clockwise ones spinning next to each other, they're kind of like trying to put two north ends of a magnet together. They won't stay close. Okay, that's not something I'd test you on, but you're going to wonder why I'm drawing arrows and one goes up and one goes down. They represent electrons that spin in different directions. Okay, so I've got these 6 electrons of carbon that I got to place, and I'm going to always start at the lowest possible energy level. Electrons are a little lazy, and they don't like to have to use more energy than they can get away with. Kind of like us, right? So it's going to get a little hard to draw with my little stylus here, but I put my first electron in the 1s orbital, and I can fit one more. I put another electron in the 1s orbital. And now that orbital's full. They can only hold 2 electrons each, all of them. Okay? And so I've got 4 more electrons to place, so I'm going to put one here. And look, I can put another one here. Okay, so now that's full. Okay, now watch this. This gets a little crazy. I got 2 more electrons left to place. Okay, so I'm going to put one in my, what would be my 2px orbital. Right? And now I've got one more to place. And some of you guys might think like, oh, we'll put it right next to its little partner here. I got an extra space in that 2px orbital. Well, guess what? This next electron, the 6th electron, is thinking to itself, dude, I don't want to have to share a space with another electron if I can help it. And do you notice how all of these 2p orbitals, 2px, 2py, and 2pz, are all at the same relative energy level? So this last little electron here, in this case, can actually safely, without having to use more energy than it otherwise would, move into that next box over and have its own space and still be on the same energy level. Okay, now what I could not have done is said like, oh, here, we'll put the electron up here because it wants its own space. That doesn't work because 3s is at a higher energy level than 2p, right? So gotta erase that. I can't do that. Okay, but if I can spread my electrons out so they each get their own little box, their own little orbital, without moving them up in energy on the diagram, then I'm going to do that. Okay, so the electron's first priority is to be at the lowest possible energy level. Okay, as low down on the diagram as they can be. But their second priority is, if possible, while not moving up in energy, to have their own space. Okay, so I don't know, let's try one more. Okay, I'm going to erase this. Oops. Okay. Oh, I can't erase it. Okay. Okay, so let's go from here. Let's imagine that we're doing sulfur. Excuse me, sulfur sodium. Okay, so sodium's got a mass of 23 and an atomic number of 11. Okay, so we've got 11 electrons to place. Well, just like carbon, the first 2 would go in 1s. The next 2 would go in 2s. So 1, 2, 3, 4. The 5th and the 6th. Okay, the 7th, look, I could still place it without moving up an energy level in its own space. But now with the 8th, remember, I cannot go and put the 8th in 3s because that's moving up an energy level and there's still technically space, even though it means sharing, in the 2p orbital. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it's not until those are all partnered up that I can put the very last, the 11th electron, in 3s. Okay? So we will talk a little bit more about this and practice some of these the next time that you are in class.